The Clausius-Clapeyron Equation. There's a little bit of maths involved in this lecture, so anytime you wish to pause the video to think about it, then feel free to do so. Before we look at this equation, we need to define some terms, and one of these is the specific entropy. The entropy per unit mass of a system, so it's just big S divided through by m. Remember that entropy is a measure of the quality of energy. Low entropy corresponds to high quality energy, that is an ordered system, and high entropy to a low quality energy or a disordered system. The Clausius-Clapeyron equation deals with equilibrium curves, that is equilibrium curves between two phases of a substance, which we'll label I and J. We can talk about mechanical equilibrium, which is equilibrium between the pressures, so Pi is equal to Pj, thermal equilibrium, where Ti equals Tj, and something known as chemical equilibrium, where Gi is equal to Gj, and lowercase g is the Gibbs free energy per unit mass, so it's equal to lowercase u, the internal energy per unit mass, P alpha, alpha is the specific volume, the volume per unit mass, and minus Ts, where S is the specific entropy. We won't derive this equation, but you'll find it in a number of thermodynamics textbooks. For those interested, you need to define something known as the Helmholtz function and differentiate that twice. So consider two phases of a substance in mechanical, thermal and chemical equilibrium. It can be shown then that dP dt, which is the rate at which the equilibrium pressure between two phases I and J changes with temperature, is equal to the differences in the specific entropies divided through by the differences in the specific volumes. That's obtained from the first law of thermodynamics, as I say, and forming a particular function. Entropy can be related to heat divided through by temperature, and the differences in the specific entropies between the two phases is related to the amount of energy you need to supply to change the phase. And so this middle term can be rewritten as the latent heat for the phase change between phases I and J divided through by the temperature multiplied by the differences in the specific volumes. And this equation is referred to the Clausius-Clapeyron equation, which, as I say, gives you the equilibrium curve between the two phases. So now let's consider different phase changes. For water, we find the specific volume of vapor is very much greater than the specific volume of the liquid, and likewise the specific volume of the vapor is very much greater than that for the solid. And hence for equilibrium with water vapor, we can write the two equations for the liquid vapor and the solid vapor equilibria for dP dt by ignoring the lower specific volume terms. So dP dt for liquid to vapor is approximately equal to the latent heat between liquid and vapor, that's vaporization, divided through by the temperature and the specific volume of the vapor. And you can use the gas law, the ideal gas law, for the vapor and replace alpha with P RV, the specific gas constant for vapor, and T. So you end up with the term on the right hand side. Likewise, for the transition between solid and vapor, you end up with dP dt solid to vapor as approximately equal to the latent heat between the solid and the vapor phase divided through by the temperature and the specific volume of the vapor. And again, you use the ideal gas law to replace the specific volume alpha. Now these are exponential looking curves. And why is that? Well, if we take the pressure on the right hand side and take it over to the left hand side of the equation, you'll have dP on P, which integrates to d log P, or can be rewritten as d log P, and when integrated gives you log P, and then you can take the exponent, natural exponent on both sides, and you get P is equal to an exponential function as of 1 on T. So both of these will look exponential like, and you'll see that in another video. What about the transition between ice and liquid water? Well, we find that the specific volume of liquid is less than the specific volume of the solid. Remember, ice expands and sits upon liquid water. And hence near the triple point we have also that the fact that the latent heat, SL, its magnitude, divided through by the differences in the specific volumes is very much greater than the temperature. And what does this mean? It means that dP dt, its magnitude is very much greater than 1, so the line is very steep. And because the specific volume of the solid is greater than that of the liquid, the terminal denominator is negative, and so dP dt is less than 0. So the fusion, that is the melting curve for water, is negatively inclined, and it's very steep. And we'll see that in another video.